Hi, we will now continue on the part 3 of the voltage control, and we will now look at the development of the nose curve equation, where we have already actually developed it, but we will now like to visualize it also. So to the right hand side here we have the previous equation that we developed, this secondary equation, and we can from that equation we can write it in a different manner. If you look on the left side here, so now we just have split it up with e squared divided by 2, and now divided by 2 on qx, so 2 is disappearing from there. And then this means that y, as I said previously, is equal to voltage in square. So that means actually voltage is equal to, then we have taken the root of the whole expression above here, and we will come down to this equation here, where is actually the equation for the nose curve. So you can see you have a square root of the whole equation, and you also have a square root of the inner part here. And we also seen what was the physical solution on those inside here. Now to see some extreme points on this curve. Firstly, we can assume that the reactive power is 0. This is 0. And then only active power consumption is done at the load side. If you do that, the equation then simplifies down to this here. Then often we do a normalization with the E, the voltage at generation side, because what's happening on the load side in such a system like this will always depend on what's happening with on the generator side. So let's take it from there. We can then continue to do the normalization. We take then the U divided by E, and then we get 1 divided by E square root multiply C, and we have E square half plus minus like this. We can do, we'll do several steps here now, just to simplify it. So now we have removed the, we're breaking it up now, the equation. So we can see that we have taken this 1 by root, let's see, I missed something, yeah, the E, yeah. 1 by E, square root of E squared, like this. Let's further develop it. Like that. Let's continue. Half now. Goes here. Plus minus. Yes, then we continue. Half plus minus so this, and then we get it inside the square root for e to the power 4 minus e to the power 4 that. Then this goes off, and then we have e equal half plus minus 1/4 minus b squared e power 4. And we are almost there. We take it to one final time here now. UE C half plus minus then 1/4 minus p squared e 4 2x square like this. Because we want this like this is due to e in 4 square equals e power 2 to x square means the short circuit power in square. This is how we should look for this, and then we can write it up u divided by e equals half plus minus 1/4 minus p. It's a typical fashion where we write this nose curve. This is without reactive power in it. So this would then be the nose curve expression represented by the active power divided by short circuit ratio. Here you can see. So if we then draw this figure, see this and this. We can try to see. Something like this. Nose curve. Here we have the U divided by E. Here we have P divided by S. Short circuit like this. And then we can actually identify the critical point. I mentioned that before with the power angle relationship, but now we also have a critical point here with the voltage power relationship. So this we call the critical point. And the critical point you can find by setting this expression to 0. If you do that, you can get, yeah, I can do it over here. Let's see, square root 1/4 0 means equal and P half. That means this should be half 0.5, and it's the one critical point. The other will be UE. Half plus minus 0, putting the, because now we're out of this point. This is U divided by E equal 1 divided by square root of 2, or 2 by 2. Can you also write it like so? This is, that's the point for the, so the critical point without any reactive power, general basis, is half of this amount here, and it's square root of 2 divided by 2 on the voltage. And this is around 0.007 value. Now let's go up and bring down the same equation where we had also reactive power in it. It was this equation. And let's copy this. So this, as you can see here, is without reactive power. Now we will have a more general curve. Equally, here, there. Now let's take this to let's see, normalization also. This, and then we get the following expression: U E equal, not U. Okay, sometimes I use U also, or V will be the same. It's just different notation. But I will try to remember to use V in this now. Equal the square root half minus QXE squared plus minus 1/4 minus x cubed squared. Now we have the following relationship. Tangents to C equals Q on P equals Q divided on square like this. Remember that angle Phi is P Q S in the power triangle. And this now we get a more general equation that is more representative and easier to use actually. So if you look at this equation, this is actually the 1 divided by the short circuit ratio here. And then we can use this tang-phi relationship both in here and here. And if you do that, and also remember that, that cos phi is P divided by, that's a power factor. Okay, let's have general equation, and it becomes like this. Finally, equal half minus P. One, 4. Like this. So this is the general equation for the nose curve. So if you have plotted down this equation we have up here, and then we will get this. This is the nose curve. And we have seen that when we have cos phi is 1, that means no reactive power is in the grid. We have, as before, 0.5 and another color, and then something like this, 0.0, like this. But now we can represent it as power factor curves, as you can see. So when we feed in more reactive power, it becomes overcompensated, we are saying. Then this curve tends to go upwards. The end point of this tends to go upwards. If you see here, we can draw here. And in the undercompensation, that becomes lesser than 1. On this, let's see. Okay, you can't do it. Yeah, okay. That's the undercompensated values. So this is how you can like develop the curves. And as you see, you have the 1 per unit voltage here. Typically, the voltage should be in the range of 0.9 and 1.1, like here to here. When we then compensate our grid system, you see that we will get actually this critical point, we call it here, will get higher, and it will get closer to the nominal voltage. So for example, if you look at this, the nominal voltage is actually here. One thing I not mentioned is that the red part of the curve means infeasible solution. So it's only the blue part here that will have feasible solution. Even though you have two mathematical solution, it's only this on the blue curve that will have a stable operation point. Below, it will not be stable. Because if you have low voltage, you will have high current, and vice versa. So here, for example, you have a higher voltage. Here, that means lower current. So one thing that you should remember that is we can see on this curve is that we can have problems with instability. That means that the voltage range in a grid system describes how good the system are. But however, as we push more and more overcompensate the equipment in the system, we will get this endpoint closer to nominal, as I said. That means that you can actually operate around here, but what you don't know is that you are actually very close to blackout or instability problems in your grid. And that is one thing that is challenging by increasing this endpoint. So you need to be careful. When you are here, you see that you will have started the gradient will start before, so you know that you are approaching earlier on this curve.